much. Thank you for the invitation. Is it working, the microphone? Yes, okay. Okay, so yes, the goal here is to present quickly a POC that we have done with MBDA about deploying quantum TLS communication between the embedded world. So first of all, what was the goal of this project? So it was not really satellite, but it's very similar in some sense that we have embedded system, we have low power cards, low power CPU, and the goal was to establish connection between two such cards with Cortex M4, M7 processors, and also a link between this card and central and control unit, which was in this case simply a laptop. And we want to have post-quantum cryptography, that is to say, cryptography which is resistant against quantum computer. So this is really the goal of this talk, to show what we have to do to enable such a communication. And so for that, I will speak very quickly about the context around post-quantum cryptography and why it is important to start very soon. In fact, as you know, probably in cryptography, you have public key cryptography and symmetric key cryptography. And in fact, with a powerful enough quantum computer, you can break all the algorithms which are used currently in public key cryptography. And so, of course, it is a big problem because public key cryptography is used almost everywhere. And so there is a huge impact. And so here we mentioned some application of public key cryptography. Of course, when you are using HTTPS, when you start a VPN, even if you are using a messaging application and so on, everywhere you are using public key cryptography. Even in blockchain, for instance, you are using public key cryptography. So one question that we have very often is when a powerful quantum computer will be able to break current cryptography. So for that, we are not expert in quantum computers, but we rely on some studies. For instance, here we show the EBCG study explaining that around 2030, there is a quite important probability that we will have a powerful enough quantum computer to break this cryptography. And moreover, the second problem is that even if quantum computers are not already available today, when you build a system, when you send a satellite, for instance, it's not only for 2 years. So you have to anticipate the migration from standard cryptography to post-quantum cryptography. Also, now from just a big some overview of what happened in standardization bodies, because it is very important for cryptography. So probably you are aware that NIST in the US start a competition to renew completely public key cryptography. So it's quite, it was a major event in the field. And last year, they already select 4 algorithms to be standardized, and and the goal is to replace existing cryptography by the new by these new standards. So it's very important to know that already last year some draft of some FIPS document were published. So now we do not speak about science in labs, but already the standards are almost there with these new crypto systems. Okay. Just very briefly also to mention what happened, especially in the US. Things are moving very fast in the US. For instance, you have some executive order from President Biden, from the White House, to promote this post-quantum cryptography. And in fact, federal agencies, it is mandatory for them to move and to have a roadmap for the migration toward post-quantum cryptography. So, and it is also, for instance, in the law in the US that you have to use post-quantum cryptography. So in Europe also you have some messages from agencies. So here you see the message from ANSI saying that in fact two things. So you have to move very quickly to post-quantum cryptography. In fact, the message is not exactly this. The message is not to replace exactly existing public key cryptography by this new post-quantum cryptography, but to work in hybrid mode. That is to say, you should keep existing cryptography and to have a second layer of keys with the new post-quantum cryptography. So this is called the hybrid mode, which introduces a lot of complexities, but also the guarantee that you will not decrease the existing security. So this is what is recommended in the next years meaning up to, for the next 10 years, we have to deal with this hybrid cryptography. So we have also very similar messages from the BSI in Germany, for instance, and more generally in Europe. The message is to go very quickly and to begin to work on this post-quantum cryptography to see the impact of the transition, because as we will see, there is an impact on the infrastructure, and especially in the embedded world, sometimes it is not possible to move from standard cryptography to post-quantum cryptography because simply it is too costly. So now I will go back to the original POC that we have done with MBDA, and just to show all the components that you need to upgrade to go from standard cryptography to post-quantum cryptography to establish this TLS connection, a very simple TLS connection between 2 points. First of all, of course, you have to upgrade your software. And so for that, at CryptoNext, we develop a 4 layers solution. Of course, we have a first level, which is the implementation of post-quantum cryptography. Here we have a very careful implementation of existing standards. We have also supporting various processors, operating systems, algorithmic improvement, and resistant such channel attacks, for instance. But this is only one layer. After that, you have to move to the protocols. So, for instance, we speak about TLS, but there is also certificates. So you have to upgrade these protocols so that you can now work with hybrid cryptography. That is to say, not only with one certificate, but with 2 certificates, or not only with 1 key, but 2 keys, and so on. After that, you have to upgrade all the existing really specific security software solutions. For instance, just to mention a few of them, OpenSSL or Bouncy Castle for Java. And the last layer is really to upgrade the final application. So for instance, if you are using a PKI to generate the certificate, you need to have a PKI which is able to generate post-quantum algorithm. Here I will focus only on this POC that we have done with MBDA. But of course, there is a lot of other applications. And really, the goal is to show you what we call the domino effect. That is to say, you don't need to, you have to modify not only one point in the chain, in the security chain, but when you begin to say, okay, I want to go now from standard cryptography to post-quantum cryptography, you have to replace many parts of the systems. So yes, to focus now on the TLS application, the goal is to have TLS 1.3 communication with double key exchange. So usually you have 1 key exchange to perform your cryptography. So here we will keep existing legacy cryptography, and we will add another layer to make a double key exchange. And the same for the authentication. So for here it was mutual authentication, And for mutual authentication, now we will have double authentication, one classical authentication with standard certificates, and a new layer of authentication with post-quantum algorithms. Of course, to do that, what we do at CryptoNext, we are very active in this standardization organization, especially in the US. For just to mention a few of them, we participate to IETF, ITU, to follow the new RFC on this post-quantum standards. We participate with IETF to be sure that what we are doing is compatible with other vendors, especially US vendors. And just to give you an idea of the complexity, you have to know that in these standardization bodies, there is already not less than 8 formats for the X509 certificate in hybrid mode. So there is not only one way to hybrid the classical cryptography, the traditional cryptography, with the post-quantum cryptography. You have a lot of variants. Some certificates are retrocompatible. Some of them are not retrocompatible, and with a lot of variants. Another layer that we need to modify for this just simple POC is the following. First, we have to modify the algorithm. Of course, the post-quantum algorithm. You need to have implementation of this new post-quantum algorithm. But also, just to mention something else, usually for TLS communication, you rely on the Diffie-Hellman principle. Unfortunately, with post-quantum cryptography, Diffie-Hellman does not exist. So you have to replace this with another mechanism, which is called KEM, key encapsulation mechanism. So you have to change something in the protocols. Also, just to mention another aspect, when you sign a message with standard cryptography, you have to first hash your message and then sign the message. Now it is no longer possible to do that, since the hash function is included in the post-quantum primitive. So it is at the algorithmic level, you have a lot of things to change only at this level. After we go to the TLS, to the protocol. So as explained before, we need to change the protocol to do this hybridization. From a software point of view, we have several implementations of this post-quantum TLS. We have a generic solution based on OpenSSL, but for the embedded world, it was too costly to use this implementation. So we have to upgrade a version of embed TLS, which is more convenient in the embedded world when you have constraint on the memory and the power usage. And also, yes, this implementation, we don't need to have an operating system to run the software. And we have also low-level interface with the hardware. And the last thing not to forget is that also you have to upgrade your PKI. And so for this project, we take a version of EGBCA, and we upgrade this version of EGBCA to be able to generate the hybrid post-quantum certificates. So you see already for this a simple project like that, you have to upgrade many, many parts. So at the end, the POC was a success. It was running very well on the card. It was reasonably fast. It was also the opportunity for the client to test what is called the crypto agility. That is to say the fact that now you have not only one standard to perform a key exchange or to sign a message, you have several algorithms. So the ability to switch really easily from one format or from one algorithm to another. And in addition, we also provide many other useful things for the end user, but I will skip this part. So now I want just to very quickly to show you that in addition to this first version of the POC, we can work in other direction. For instance, there is two aspects. The fact that post-quantum cryptography is more costly, and so we have specific implementation when the memory is limited. So I will show you the impact of the new version of the library, which is able to run when you have very low memory. And the second thing is the resistance against side-channel attacks. So you will see that, yes, it is possible to be resistant against these physical attacks, but there is a cost to pay. So first of all, for the low memory implementation, sometimes in the embedded world, you have not megabytes of memory at your disposal. And so in this case, we have specific version of the library, which is able to run with really low memory. So for instance, here you see, it's one example with the dilithium at level 5, the maximal level of security. Usually you need this amount, more than 100 kilobytes of memory to run the code. But you have a version which is able to run with only 9 kilobytes of memory. And sometimes it is really mandatory to have such an implementation. Of course, there is a price to pay, but which in this case is not too much. There is an overhead of 2.4 when you want to use this version of the library. So just an example that, yes, okay, in the embedded world, sometimes you have not enough memory. Now, the second problem is much more important. It is the resistance against side-channel attacks. So side-channel attacks, you know that if you can have access to the hardware, you can extract a lot of information. And so you can have a very good mathematical algorithm, but if you have a poor implementation, you will leak a lot of data. So it's very important to have a very secure implementation against these attacks. And just to give you an idea, please do not try to read entirely the slide, but just to give you an idea, at some point in the code, in the algorithm, you need to check that a ciphertext is equal to another one. So it seems to be very simple, and when you have not to be resistant against this side-channel attack, it is very easy to implement in any computer. If C is equal to C prime, then I can do something. So here you have the original code with no masking, and here you see what you have to do when you want to mask, that is to say, when you want to protect this code against such channel. So you see, from one line, now you have more than 20 lines, and here, I will not explain, of course, but you rely on a lot of other functions. So you are going from very simple code to very complex code. And to do that, you have to, in fact, change your implementation to split the data into several parts to protect against these side-channel attacks. And so one question is, so it is known how to do that, but you have to decide also at which order you want to protect your code. So again, I will not speak, don't try to read the slide, but just to show you that there is a lot of activity in this area. And so, for instance, some paper claim that using AI, they can attack protected implementation, even if there is a protection at order 5. Okay, so you can say, okay, but then the solution is to have an implementation of all this algorithm with a protection at order 5 or 10 if it is needed. And the question now is, what is the impact of this protection? So here I report some implementation. So again, things are moving very fast in this area. So here you see the blue curve. It was an implementation. It was a paper in 2021, so not very old. So you see that here on this axis, you have the masking order. So here, when you increase the masking order, you increase your protection. But of course, here you see the time takes by the implementation. And so you see that only at order 3 on the blue curve, you already have a factor of 100, meaning that the implementation is 100 times slower than the original code. So you see a huge impact. So things are moving. Here you see a more recent paper. So you have still this exponential behavior. So when you increase the security, you have to pay the price. And this price is quite high. So you see, if you want to resist at order 5, you have a factor of almost 40. And the problem is that you have this factor of 40 on a very low power processor, which is already very slow, usually. And so you need to multiply the timings by 40. So just to show you that this transition between classical cryptography to post-quantum cryptography is possible, we demonstrate this with the successful POC. But you see also that in some case, you have an impact on the hardware. You have to decide, for instance, to upgrade the frequency of your processor or to change the processor that you want to use in your system. And so, in conclusion, I think you understand that it's really very important to start this journey on this post-quantum transition, that there is not only one piece of software to replace, or a piece of hardware or software. You have to upgrade many, many components, and you have to see the impact when you change a certificate. For instance, if you replace all your certificates by something which is not retrocompatible, you will break completely your infrastructure. Or you see that in the case of the embedded world, sometimes the hardware, existing hardware, will not support simply the transition from standard cryptography to post-quantum cryptography, simply because it is too costly. And so, yes, I would like to conclude this presentation by asking you, in fact, in this transition journey, where are you? Did you realize that it is very urgent to move and to begin to really understand what is the impact of this post-quantum transition? And in fact, my conclusion is, where are you in this transition? Thank you.
Thank you so much for the talk. That was really interesting to see where post-quantum crypto is, especially regarding side channels. Do we have any questions from the audience? I guess then I asked the big question, when do we have quantum computers?
As explained in the beginning, we are not experts at all in post-quantum computer. So the answer is, I don't know, but do you want to take the risk not to take into account this threat? So this is why, in fact, we rely on some studies. So some people say that we will have quantum computers next year, for instance. Some people say in 2030, and some other people say it will never happen also. But this is really a risk.
It definitely is. Thank you. Any other questions? Oh.
Hello, great talk. Maybe I didn't quite catch this, but what do you think about the directions in the industry at the moment about hardware mitigations to side channel attacks? I mean, do you think that firms are doing what is necessary to mitigate such attacks, or maybe they are not taking them into consideration because hardware design is costly? What is your opinion about that?
Yes, it is costly, and also you see that a lot of these new standards are very new. So, of course, when you want to go to hardware, you need to have a stable standard, because you cannot afford to design and to redesign everything every month. So this is probably why hardware were not so advanced compared with software as usual. But of course, we see that when there is such an impact on the performance, at some point, we need to have hardware implementation. It's mandatory, in fact. So this hardware implementation for various aspects which are used in post-quantum cryptography will happen and begin to happen already with some hardware vendor.
Thanks.
All right. Thank you so much for the talk.